All right, so here's a video continuation from class 7. This is video 5 of fluid mechanics. And here's an example out of our book, Sengel. This is example 5.2, where we have a 4-foot high tank, 3-foot diameter. It's cylindrical, and it's got a water, it's carrying water, and this top is open to the atmosphere. It's filled with water, and the discharge plug near the bottom of the tank is been pulled out, so that there's a water jet whose diameter, or maybe even effective diameter, we'll learn that there's something called the vena contracta, I think, so that we'll see what the diameter can be estimated that way. 0.5 inches, it streams out, and the average velocity of the jet is given by the equation v is equal to the square root of 2gh. By the way, if you're keeping track or you would like to know, that is also known as the Torricelli equation, and we could find it from Bernoulli. So we could actually get that later. Where this h inside, that's the height. It's like an adjustable height of the water, right? So it's a variable, and the tank, and it's measured from the center of the hole, right? Even though it's not shown that way, that's okay. And g is the acceleration of gravity. We want to determine how long it will take for the water level to go from the 4 feet high that it starts at to the 2 feet. So this one is a Reynolds transport theorem applied to your conservation of mass, right? So conservation of mass, COM. And what we have going on here in terms of the tank, we actually do have a 0 is equal to dm of the control volume dt, right? And then that's going to be plus m dot out minus m dot in. Trying to make it look a lot like some of the stuff that we had when we were doing the equations for the conservation of mass, but let's see. Where'd we go? Yeah, it's basically this equation right here. Maybe with a little, this right here represents this portion, whereas this right here represents these two portions right there of the mass flow. But because this control volume is actually changing with time, that's why we write the equation out that way. And my paper's all in different order now. Great. So let's take a look at the various parts of this. First off, I'm going to start out with the mass within the control volume, right? So the total mass in the control volume, right here in the beginning, but let's just get it in terms of that we can use, would be the density times the volume, and so that would be the density times the area of the tank. Maybe I'll write tank right there, and times h. And we might also, maybe I'll continue this down, density times pi over 4 diameter of the tank squared times h, right? But h can vary, right? So we might want to keep that in mind. I'll write that as mcv. And okay, sure, let's say that. So this is something we're about to take the derivative of here in a second with respect to time. And the only thing that's variable with time, right, the dmcv with respect to time, density doesn't change, pi over 4 doesn't change, the diameter of the tank, but the h does, right? So we can replace that thing with rho pi over 4 d tank 2 dh dt. And that'll be helpful to us in a second. Let's continue with the rest. All right, so we have the m dot out. And that might as well be the m. Okay, so m dot in is going to be 0. Maybe we should write that somewhere, because there's no valve or refill right here. All we got is m dot out. So m dot out, we already know that that's going to be, trying to look for the thing, that's going to be density times the area of, velocity times the area of the jet, right? Which we know right here is going to be rho times the square root of 2gh times pi over 4 diameter of the jet squared. Do I want to massage that thing around? I think I can start plugging things in. All right, so I'm gonna have, I have this one and I have this one. Let's plug these back up into this original thing. And we also have in is out. Is that okay? Yes, yeah, we're gonna be fine there. Yeah, we'll get the correct signs. So I'm gonna write that I have rho pi over 4 d of the tank squared dh dt plus, maybe I'll take my pi over 4 and move it over here, my d jet squared, and my square root of 2gh equals 0. A couple things I can get rid of my rho's, get rid of my pi over 4, and rewrite this thing. So I'm going to bring, do I want to do that? Sure, let's move everybody around a little bit. So I'm going to take my dt and multiply it. I'm flipping this guy over to the other side. I'm lazy. I guess I'll do it, and you can verify this yourself that we could manipulate this thing into this form right here. And I'm going to move this 1 over square root of 2gh and have dh. So now we can integrate this. These two are constants. I could even move that 2g out of there if I wanted to. And so I'm going to go from 0 to time. So generic time, and then I'm going to start with this guy. And notice it's going negative, so that's going to help us here in a second. We're going to get rid of that negative by way of this integration, by the nature of the problem. We're going to go from its original height to its final height. So we're just going to get time over on the left-hand side, and we're going to get a very lazy man that I am. I want pulling out the 2g, and that we're going to have d tank squared over d jet squared, and 1 over square root of 2g. And then when we go to take the integral of this, right? Yeah. I'm going to have to, well, let me, all right, let me go ahead and do that right there. Okay, I'll go from HO to H. And I'm just messed that up. I'm sorry. I'm going to keep it though. I'm going to keep it. I don't have time to, I don't want that integral. Come on. Here's what I'm trying to do. There you go. This is just a constant on the outside. HO to H, and we're taking H to the -1/2, right? Because he's on the denominator, and so we have DH. And when we do that, we're going to have to add this and then multiply it by 2, right? So we're going to add 1 to it and multiply it by 2. So what we're left over with is going to be all of this. Okay, I see what happens, because this guy right here is going to go from 4 to 2. Yeah, I guess I gotta put that in. I'm messing this all up. Am I tired? All right. So what I have here is my tank squared over d jet squared, and then square root of h, but it's going to be got it 2 divided by the square root of 2g times the square root of h from 4 to 2, right? And because it's going to be 4 to 2, that's going to make the negative go away, right? Yeah, okay. This is just going to reverse the order of these things. So I think I'm about to get it right, where I'm going to go d of the tank is 3 feet. D of the jet is going to be 0.5 divided by 12 squared, sure. And yep, we're going to have 2 divided by the square root of 2 and 32.2. And everybody else, sure. We're going to have square root of 2 minus the square root of 4. And with all of that, we're going to need a time of 757 seconds. And we can divide that by 60, and we'll have a time, I can move the camera, not the thing, of 12.6 minutes. But let's reiterate, let's see what we did right there. Because we just tried to find how this thing is a function of its height, right? So its velocity is a function of its height, and we're going to find out soon that's going to come from Bernoulli. But we talked about a control volume. We want to see how this control volume was getting smaller, and so that's this part of that Reynolds transport theorem. And then we have mass coming out. We could have mass coming in, but we don't. So we set that equal to 0. We establish with that we could get the densities to cancel out down here. And we're rewriting this thing, and we want to move it around so we get it as a function of height. We know that that's changing with time, and so we're able to integrate and be able to find the time. So that was an example from Sengel. Good book. You should buy it. The end.